Okay, as you remember, we were talking about memory system challenges, opportunities, and some ideas. Today we're going to continue that and then jump into memory-centric computing. Before that, can everybody in the back hear me well? It's all good? Okay, it's not too loud here? Okay, I'm carrying 3 microphones here, so I feel like I'm a ticking bomb. Yeah. Okay, so this is the agenda, and we haven't finished topic 1 yet. My intent is to finish topic 1. I'll introduce some things that I think are important to introduce also, based on the questions that I got during the breaks, and then we're going to jump into memory-centric computing. So this is the slide that I left you with. We were talking about a lot of challenges, opportunities. This is one challenge that we're not going to go into detail about. Today, we have a lot of computation units, cores, accelerators, whatever you want to call them. And they're all connected to a single main memory or a collection of main memories. And these cores, when they access memory, they interfere with each other, which means that they cause each other delays. And this is the memory interference problem. And if you don't control this interference carefully, this leads to many problems like quality of service, performance, predictability. One core can deny service to another core, for example. And this is a major issue. That's why people design memory controllers in very careful ways, although there's a lot more to do in this area. So I don't want to go into a lot of detail into the solutions, but this problem is getting much worse because our systems are becoming more complicated. As you can see over here, there are general purpose cores, there are more special purpose cores, hardware accelerators, there are GPUs, and there's sharing that happens at different levels. And then memory is also getting complicated. You can see that there's heterogeneity. We discussed that last time. We're going to discuss it a little bit more today. And there are many goals, many constraints, many metrics, because the quality of service that you want to provide, it really depends on what kind of application is running over here, right? If the application is very user critical in terms of interactions, the quality of service matters a lot more than another one. And how to allocate resources to these heterogeneous agents that are accessing memory to mitigate interference and provide predictable performance is an important problem. So I think this is where I will leave you with. There's a lot of work in this area that I'm not going to cover. It's in past ACACES courses that I've delivered. But in the end, memory controllers are critical to research, and they will become even more important. Because they're really, from my perspective, they're really the center of the world. Like people think processors or accelerators are the center of the world. I think memory controllers are really the center of the world because everything goes through the memory controller. Whereas if you look at the processor, some applications run there, but some other applications run somewhere else. But everything has to go through the memory controller to access memory in the end. Okay, so this is one work that we may cover in the last lecture, which is if things are getting so complicated, maybe humans are not good at really dictating policy in these memory controllers. And this is what we had in mind when we wrote this paper in ISCA 2008. We used reinforcement learning to control memory. And I think there's a lot more to do in this area, but hopefully we'll leave that for the last lecture. Okay, now now that we've introduced challenges, opportunities, and trends in memory, let's talk about how we can solve the memory problem. So I'm going to give you some broad directions, and then we're going to jump into some examples, and certainly we're going to jump into memory-centric computing a lot. So how do we solve the problem? I think there are 3 major directions that are interesting. There may be more, so please feel free to talk to me if you have ideas. One is we somehow need to fix it. Of course, what does it mean to fix it, right? I think fixing it, from my perspective, is to make memory and controllers much more intelligent than they are today. Today, memory is treated as a dumb device, meaning you do loads and stores to memory, you get data out, and then you do refresh, that's it. You cannot talk to memory as an intelligent being, let's say, right? It cannot do any computation, for example. It cannot really satisfy guarantees. You cannot tell memory, please do this function for me, but just bother me whenever it's done. I don't want to care about individual loads and stores, etc. Right? We cannot do that today, basically. And as a result, I think we're kind of punishing ourselves with this important part. So for this, I think we need to examine new interfaces to memory, new ways of talking to memory, new functions to execute in memory, and new memory architectures. I call this system memory co-design, and we're going to talk a lot about that. And memory-centric computing is part of it. The second thing is somehow eliminating or minimizing the problem. I think this is very difficult, but there could be some approaches that could replace difficult to scale technologies like DRAM with different technologies. The jury is still out on this one. I think this is a very important research area. People, especially in academia, should be doing this sort of research so that we can have some sort of memory technology 10 years, 20 years, 30 years, 40 years down the road. That's actually very important. but it's not an easy area, it's a speculative area. So I think this could enable new technologies like phase change memory, for example, and it could enable a system-wide rethinking of how you actually organize memory and storage. We'll talk about that a little bit, but as I mentioned, this was the subject of 2013 and 2018 lectures, and I don't have time this time. And the third direction I think is also very interesting, is somehow embrace some of the problems. Maybe not everything, but for example, if the memory cannot be made perfect at all metrics, for example, reliability, performance, latency, bandwidth, you cannot get all at the same time. Why don't you design some heterogeneous memories? Some of them may be less reliable, but they may have a lot of capacity. They may also have low latency and low voltage, low energy, because you're making them less reliable. And some memory is much more reliable. And somehow embrace the problem by punting it to the higher level system. Somehow understand what kind of data can go to what kind of memories and allocate that data intelligently to different types of memories. I'm going to give you an example of this one, but I think this is very important and it's going to be even more important in the future. This is kind of happening a little bit today. Okay, there may be more solution directions and I'd be happy to hear your opinions in the breaks, etc. So in the end, I think if you really want to solve the problem, you need to think across the stack, because none of these are at a single level. You really need to change some of the interfaces, functions, technology, and models with which you're managing data with. Okay, so you really need to think across the stack, I think. So let's take a look at the first solution direction in a little bit more detail. So how do we overcome memory shortcomings? I think you need to think memory as a first-class component in the design. Today, it's not thought as a first-class component. It's always second-class to the processor. Processor is the king, and memory is something that serves the king. Right? I think we need to really change that model going into the future. Everything that was that is built for machine learning accelerators, for example, we're building these complicated hierarchies for the king, which is the machine learning accelerator. I would argue that that's the wrong way of designing systems. Okay, so for this, I think we need to look at novel memory architectures, interfaces, and functions, and also we need to examine the waste we have in memory. And memory has a lot of waste, actually. So there have been a lot of works that show that, let's say 30, 40, 50% of your memory is storing zeros. Does it really make sense to store zeros? Per Stenstrom had a paper, for example, at ISCA in 2005 that showed 30% of main memory in general purpose application is all zeros. So you can actually compress memory much better. Memory, there's also a lot of issues with bandwidth, meaning internally memory operates at very large granularity, but we get very little amount of data out of it, meaning that there's a huge waste of energy inside the memory also, because we read memory at very large blocks. I may talk about some of these. So I think we need to think about the waste that we have in the system. So there are many key issues to tackle here. This is a laundry list. How do we enable reliability at low cost? This gets us high capacity. How do we reduce energy? How do we reduce latency? How do we improve bandwidth? How do we reduce waste in terms of capacity, bandwidth, as well as latency? There's actually waste in latency also. We can access memory much faster than we can today, but because there's a lot of margin added to the latencies so that manufacturers can guarantee reliable operation, we're accessing memory at much longer latencies. Again, this is not a topic that I'm going to touch, but by adapting the latency to the temperature and the chip, you can actually reduce a lot of the memory latency. Okay, in the end, I think enabling computation close to data will help a lot of these over here, because it could solve some of the reliability problems, and also it could reduce energy, latency, improve bandwidth, maybe reduce waste if you do compression inside the memory, for example, compression and decompression inside the memory. Okay, any questions? Again, I'm still painting broad strokes over here. Let's talk about emerging memory technologies. I said that I'm not going to talk about this in detail, but I have to, because I see a very dangerous trend motivated by industry. And I think in some senses we should work with industry. In some other senses we should be independent of industry, because we really need to set the stage for future generations. We cannot really be dictated by short-term concerns. So that'll become more clear when I see a dangerous trend that industry, because Intel didn't follow the Optane memory, for example, people are saying, oh, we should not work on emerging memory technologies. I have to set that a little bit straight over here. So I think there are very interesting emerging memory technologies that are more scalable than DRAM. A lot of them are resistive. They don't operate based on charge principles. So whenever you access you don't access a capacitor, for example. You check the resistance of a resistor or a magnet, etc. And these are non-volatile. I'll pick one of them, phase change memory. This is an area that we have worked a lot on over many decades. And this is a very interesting technology. You store data by changing the phase of some material. it could be chalcogenide oxide, for example, and you read data by detecting the material's resistance. There's no charge involved here, which is good, because charge is very difficult to scale and charge escapes. And these are old numbers, but there's a beautiful paper by IBM in 2008 that talks about this technology. If you're interested, I'd recommend reading that paper. And this is expected to be denser than DRAM because you can also store multiple bits per cell by chopping the resistance range into many different data representations. Okay, so the issue is emerging memory technologies are not perfect. They also have many, many shortcomings. So for example, phase change memory, it's longer latency to access, longer energy, even though it can be much more scalable and it's non-volatile, meaning you don't need to refresh it. We talked about refresh yesterday. This gets rid of refresh for most cases, let's say. So the key question is, can we somehow design these technologies to replace, augment, or even maybe surpass DRAM? So how do you surpass DRAM? By getting rid of refresh. Another way of surpassing DRAM could be, these are non-volatile technologies, meaning they could be acting as storage and memory at the same time. You don't have the distinction between main memory and storage as we have today. Today we have main memory, DRAM, storage as SSDs and hard disks. And they have very different interfaces. You can have a single interface using phase change memory to both memory and storage, such that you can manipulate persistent data like files in place. Okay, I've said a lot of things over here, but if you're interested in memory technologies, there's a lot of work in this area. This is one of the works that we have done early on. We've done more work, and I've listed that. And as I said, Intel introduced, like 10 years later, these papers, this persistent memory. More recently, they've discontinued it. And I see what happened is after Intel introduced this, in the systems community, there was a lot of excitement. Oh, let's design operating systems for this. Let's design compilers for this. Let's design management mechanisms. After Intel pulled it out of the market, systems community, oh, we should not work on it anymore. This is, I think, in my opinion, very bad for research. People should be working on emerging technologies regardless of what the industry does. Okay, I think that was my point in emerging technologies. Okay, and there are some papers that I'm not going to go over clearly. These are our papers, but there are a lot of other papers from other folks as well. Okay, but I think a more viable direction is really not a single technology, because single technology is not good at everything. I was showing you this picture yesterday, and sorry about the colors. This is not my fault, this is the projector's fault. Colors are perfectly fine over here. But basically, if a single technology cannot give you everything in terms of different metrics that you want, for example, speed, durability, capacity, refresh, volatility, cost, etc. Why don't you put multiple different technologies off a single node and design the data allocation and movement mechanisms in hardware and software to get the best of each technology as much as possible while avoiding the bad parts of each technology. And this is hybrid memory systems, and this has been happening, as we've discussed yesterday, especially with high bandwidth memory and high capacity memory. Essentially, GPUs have that. Many machine learning accelerators are going to have that. I think CPUs increasingly have that. But there will be more, in my opinion. Of course, the key question is now, this is a heterogeneous memory. And whenever you introduce heterogeneity into the system, you add complexity. So clearly, there's some complexity, system complexity, that you need to deal with to manage these memories. And there have been many works that talk about how to do this at the operating system, how to do this at the programmer level, how to do this at the hardware level, how to do this at the compiler level. All of them are interesting to examine, and there's still more to do. Okay, I'll give you one example of taking advantage of such memories. And the idea here is, if you know the characteristics of your data, then you can perhaps scale the memory system to be very large, and not all of it needs to be reliable. So it's well known that applications and data have different characteristics in terms of memory error vulnerability. So if you get a fault in memory, in some critical data structure, you can get a crash in the application. That's a vulnerable data or vulnerable application. Some other data, you get a fault in memory, nothing happens. You don't care. Maybe a pixel goes wrong and nobody notices it. So if you can characterize your application data in terms of its vulnerability to different faults in memory, like this could be a continuum, of course. It could be vulnerable tolerant. Then you may actually treat them as different and allocate them to different memory devices. For example, one memory device can be designed for vulnerable data. It could be extremely reliable, very high cost, potentially. It could be very well protected, well tested, etc. Another memory device that houses the tolerant data can maybe not so well tested. It could be huge in terms of capacity. It could have all types of issues like RowHammer, for example. We call this heterogeneous reliability memory. And we actually prototyped this in simulation, and we found out, together with Microsoft folks, we found out that, so in data centers, you have memory with ECC. And ECC has a lot of cost, and a lot of power and energy implications, etc. So we wanted to understand, can we get rid of some of the ECC in the data center and make the memory much larger so that we can scale the applications to be to larger systems. And we found out that you can actually reduce the server hardware cost by about 5% this way, while still achieving a good availability target. So there's more to do in this area. This is not the last word, but this is really an example of the across the stack thinking. So how does it work? Somebody annotates the applications and the data by characterizing and classifying application memory error tolerance. I'm going to give you another example of this soon. And different data is classified as vulnerable versus not vulnerable. And again, this could be a continuum. And then somebody maps the application data to the heterogeneous reliability memory system via software-hardware cooperation. And somebody designs the different types of memory. For example, reliable memory may have strong guarantees in terms of error rates. Low-cost memory, unreliable memory may have much less stronger guarantees in terms of error rates. And then there could be other stuff in between that we discuss in the paper. Now the advantage of this is this could get you to a trade-off space that's much better than today's system. So typical servers today, for example, try to maximize everything. As a result, they have very high cost and they have very high memory cost. Whereas by allowing some data to be incorrect, whenever that data doesn't matter that much, you can actually reduce the cost significantly. That's what this HRML does over here. So in terms of availability and crashes, we're very close to a typical server, but we have a lot of cost savings. Okay, so if you're interested, there's a lot more in this paper. I actually talked about it more than I expected to, but you can read more. Any questions? Okay, yes?
How do you determine whether
yes.
it's critical or not? And I don't know, even if you have the errors, the quality of service is reduced, right?
Yeah. It depends on the application, basically. If yes, how do you determine? Basically, it has to be done by someone who knows the programmer. It's very difficult to do this automatically, I think. Although with machine learning, with very large analysis of data sets going into the future, potentially that's possible. Yes, it depends on the application. Your application should be able to tolerate it. If your application cannot tolerate the quality of service loss, then don't do it. I'm going to give you one application that can tolerate it, which is deep neural networks, right? That's the beauty of some of the neural networks. So we've applied this idea more recently to neural networks. And if you look at deep neural network evaluation, it's very DRAM intensive. A lot of papers show that. This paper that I'm going to show you shows that also, especially our large networks. And it turns out some data and layers in a neural network are very tolerant to errors. And the idea here is to map such data and layers to low energy and low latency DRAM, which may have more errors. Basically DRAM with a higher error rate, potentially, but it has low energy and low latency. And you get a higher error rate because you reduce the latency and reduce the energy significantly. Energy means voltage, for example. And the goal is to still achieve a reasonable accuracy level. And with DNN training the neural network, you can actually achieve this over time. Okay, by making it DRAM aware. So this is an example of data aware management of DRAM latency and voltage for deep neural network inference. Let me give you an example. So this is one particular network, it's ResNet. It's a small one, yes, but a lot of networks have these properties. These are the weights and input feature maps of different layers, as you can see over here. And the y-axis shows the maximum tolerable bit error rate for that particular layer. And you can see that some layers, and this is sorted based on the maximum tolerable error rate going low to high. You can see that some layers are not tolerant to errors, some layers are very tolerant to errors. So bit error rate is much higher over here. And the idea is to identify these layers somehow. You can do this through profiling and map more error tolerant DNN layers to DRAM partitions with lower voltage and latency. So in this particular work we did one example for DRAM partitions with different error rates. And you can see that these are the bit error rates. And you can actually design your DRAM to be customized to provide that error rate. So you can say if the DRAM designer, for example, has the ability to design a DRAM that has 8% bit error rate, they have a lot of flexibility in reducing the energy of the DRAM and reducing the latency of DRAM. One of the reasons why today it's very difficult to design memory is you have to make it completely reliable and also at the same time reasonably low latency. So you don't have much room to play with. Here, you give it room to play with to the DRAM designer. And if you do that, the idea is to enable accurate and efficient inference using this approximate DRAM mechanism. I'm not going to go over the details, but what you can do is you can actually look at error tolerance characterization of the DNN, map it to the DRAM, and then look at your accuracy. And by changing your training mechanism to be aware of these errors that happen in DRAM, you can increase your accuracy, you can boost your accuracy. This is very well known in DNN training in general, error-aware training. Error can happen due to different reasons. Quantization, for example. People do quantization-aware training. This is no different than quantization-aware training, really. Okay, so what's the benefit? The benefit is you get significant energy reduction in DRAM, while accuracy is reasonable, depending on your accuracy target. Again, if your accuracy of less than 1% is not acceptable, don't do this. If it's acceptable, then you can do it. And in many cases, especially in edge devices, it could be acceptable because you're very much power constrained, and saving 20% power at the expense of 1% accuracy may be okay because you process the data somewhere else later on. Okay, so we also see significant system speed-ups also because we reduce the latency to the DRAM, and some of these layers are quite latency sensitive. Okay, and we evaluate on GPUs and specialized machine learning accelerators and also TPUs, and we see similar energy reductions as you can see over here. And again, this is the paper. I wanted to give this to you as an example because this is another example of heterogeneous memory that could be used to accelerate machine learning. While accelerating it, you also make it more energy efficient. Okay. Any questions? Yes?
I have a small question.
Yeah.
Since the layers in deep learning is less sensitive to the accuracy, is it possible just to remove this kind of layer because
basically, is it possible to remove some of these layers because some of them are less sensitive? Depends. Again, depends on how much you impact accuracy, right? Yeah, there's a reason why people add layers, but yeah, in some of the deep neural networks, it may not be needed. But in general, it's very difficult to remove complete layers, but you can play tricks like this, like quantization, etc. Yes?
What's the overhead of using different neuron modules with different accuracies?
What's the overhead? Well, overhead is really complexity of the system, right? Now, instead of having a single DRAM, you have multiple different types of DRAM, and also you need to somehow manage them. Yes. Okay. So let me go into something that I didn't intend to cover, but I had to cover because these are all examples of something that's really important in my opinion, which is data-aware architectures. So if you look at these examples, here we are designing the hardware and the software to be aware of the characteristics of the data. In this particular case, it was the error characteristics of the data. So I'm going to go through this relatively quickly. I'm going to take, again, a contrarian view. Today's computer architectures are processor-centric. We're going to cover that. Today's computer architectures make human-driven decisions. We're going to cover that with machine learning at the end. This was a piece we were not covering in the original slides, but I think today's architectures are poor at knowing and exploiting different properties of application data because this information is not discovered at the higher level and not communicated to the lower levels in general. With specialized accelerators, this is changing, but I think we need to do this more at the general purpose level also. So basically, today's architectures are designed to treat all data as the same. They make component-aware decisions as opposed to data characteristic-aware decisions. So let's take a look at what a data-aware architecture or data characteristic-aware architecture may look like. I think the idea is to understand what you can do with and to each piece of data. So what are those? You can make use of different properties of data to improve different metrics, performance, efficiency, and other metrics. And there are many different characteristics of data. Data has different compressibility characteristics, approximability characteristics, locality characteristics, sparsity characteristics, criticality characteristics in terms of how critical this particular piece of data to the accuracy of your computation, right? Or even the finishing of your computation. It has access semantics. It has security and privacy characteristics also. So if you can somehow communicate this information to the underlying hardware, then you can actually make much better decisions. I'll pick an example from a memory controller. So side channels, for example, side channel attacks are a big deal in hardware today. And you design memory controllers today to try to mitigate the side channel attacks. If you try to do this without knowledge of the application, it's very costly in terms of overhead. But if the application somehow tells you, oh, this piece of data that I'm now accessing is security critical, and I cannot tolerate any side channel, so do something about it, that information is marked. That comes to the memory controller, and memory controller maybe takes a very different action on that one, as opposed to trying to service everything the same. And I strongly believe that this sort of marking of data in terms of its characteristics is going to be a lot more important going into the future, and security is one example of this. But there are many other examples. For example, compressibility. If you can somehow say this particular data area, data region, or data structure has particular types of characters that are compressible with a particular algorithm, then you can actually design compression algorithms internally in the hardware that are much better fit for that data. Okay, so there are many problems over here because we're really cutting across the stack. One of the problems is you cannot communicate this information in a general purpose way to the hardware today. There's the discovery of information also. How do you discover information? But at the higher level, you can discover some of these information. Like some of these are already available. Data structures, code optimizations, access patterns, data types. These are all available at the high level. But we have a software-hardware interface, especially in general purpose systems today, that's really a funnel. That puts everything as instructions and memory addresses, and instructions may not be very capable. So the idea here is to have a much more expressive interface that cuts across the stack. You have many different things at the higher levels, data structures, for example, and include annotations with different parts of memory regions, such that we can provide higher level program semantics into the underlying hardware. A general version of this as expressive memory. I'll briefly mention this. And this is the paper that really introduced it. I'll go through this relatively quickly, but there's more to do, I think, in this area. So basically, software provides key program information to the hardware, data structures, access patterns, data type and layout, but other characteristics like privacy and security that I mentioned. And then hardware does the data placement appropriately so that it, for example, disentangles things to different types of memories. So if you know some data has a characteristic that's very streaming accesses, you allocate it to a memory that's optimized for streaming. If some other data has random access patterns, you allocate it to memory that's much more optimized for random access. And you can customize memories for different types of accesses. So you could actually design the prefetcher this way. This particular paper shows an example. You can customize your data compression algorithms in the hardware layer so that it is better fit for different types of data types and layouts, for example. Okay, this could enable many optimizations. I don't have time to cover all of these, but you can express a lot of things. This is a limited set. These are actually more performance related, but there are other things that could, like approximability, like we've discussed. And then you could actually use this information to optimize, well, is that me or? Optimize a lot of things, hopefully not me. Optimize a lot of things. And the benefits are you get more efficient hardware in terms of performance and efficiency, and you hopefully get reduced software burden because the way we do it is really general purpose. I'm going to show you the key idea, how do you do it general purpose. Basically, we have an interface that interfaces the program with the hardware, and this interface is supposed to provide cross-layer abstractions. We want generality in this interface so that we can express almost anything that the programmer can come up with, not easy. And we want also to minimize programmer effort and overhead. So the approach we took in this work was to flexibly associate specific semantic information with any data. In this particular work it was data, but I think this could be generalized to code as well, like instruction memory. So what is the idea? So I already said this, I think. There's a new hardware software abstraction we call Atom for conveying data semantics. And at the high level, you have memory regions. Memory regions are associated with atoms. And this atom specify characteristics of that particular memory region. So what is this memory region? It could be at the page granularity, it could be larger, it could be smaller. Ideally, it may be at the data structure granularity, but the granularity is an important aspect of it that is discussed in this paper and in a later paper that I'm going to mention. And this information is conveyed to the hardware. So hardware knows for each memory region, these are the characteristics. And then it takes an appropriate action when it's prefetching for that region, for example. If the prefetcher, for example, again, I'll pick the access characteristics. If the access characteristics is very streaming, if you know the stride, the prefetcher easily says, oh, I'm going to prefetch this way. If the access is completely random, the prefetcher says, I'm not going to prefetch it at all, or something like that, right? So you can actually optimize the hardware much better by having this semantic information from the higher levels. There's a lot more in the paper that I'm not going to talk about how do you actually do this, but essentially you need to change the program to be able to do this. And there are many optimizations that, again, I mentioned some of them, but there's more you can find. But again, the paper is also limited in terms of what it can fit into one paper. So this is the idea over here. In the same conference, we published another paper together with NVIDIA. So we worked on a particular example of this idea on NVIDIA GPUs, and we called it locality descriptor. So it turns out exploiting data locality in a GPU is a very challenging task. You have a lot of different hardware mechanisms like placing data, managing the caches, managing the cooperative thread arrays, doing data prefetching, etc. And the application doesn't communicate a lot in a GPU. So the idea here was to have this locality descriptor communicate information about, for example, what kind of access patterns you have in this particular part, in this particular warp. And then we actually communicate this information to the lower levels. I think I've already said all of these. I will not go into a lot of detail because we have a lot more to cover, but if you actually do this, you get significant performance and energy benefits. These are some performance examples. You can improve cache locality, and as a result, you get more than 20% performance improvement. You can also include NUMA locality, non-uniform memory access locality, and figure out which threads should be allocated to which NUMA nodes, and this way you can actually get a lot more performance. So this is an example prototype that we did with NVIDIA. Later, we actually extended this prototype. We designed an FPGA-based prototype. This was published at HiPEAC in 2023, and people thought it was worthy of a West Paper Award, so thank you. Basically, this is an FPGA prototype that you can download. You can actually use it yourself. It's all open source. You can find the source code over there, which does essentially what I just said on a RISC-V processor. So if you want to actually communicate the semantic information on an FPGA prototype and see how you can optimize your program and hardware together, I'd recommend taking a look at this. And this way we were able to actually quantify the overheads of this metadata management that happens in the hardware to keep track of all of this program semantic information and use it for different purposes. In this case, we have a prefetching example. We also have a security example that does bounds checking. So if the software can communicate, for example, higher level bounds of a program, you can do much better bounds checking at the hardware so that you actually get rid of a lot of the buffer overflows, for example. So there's a lot of applications to this sort of higher level program semantic information being communicated to the lower levels. Okay, there's more examples I've already given you. There's some other examples that I did not give you, but we don't have time. These are some papers that I'm just going to keep them as reference. You can find them on slides, but we don't have time to cover them. And these are all examples of this higher level program semantics communicated to the underlying hardware. Okay, any questions? I had to cover this topic because I think it's extremely important. This will not be implemented immediately by industry, but I think over time this needs to happen in general. Okay, so this is an example of rethinking the entire stack, right? How do I actually rethink the higher level program that I am writing and express semantics such that I can optimize the lower level? So before I jump into memory-centric computing, some people ask me, like, how do I get into memory systems research? I'll very quickly give you an example. Clearly, reading papers is one way of getting into memory system research. Questioning the papers, saying, oh, this paper did something great, yes, but don't stop at great. What did it not do? What is the limiting part of this paper? If you critically analyze that particular work, what would you improve? So that's always a good approach into getting into memory systems research. Okay, now you've done that, you have an idea, or maybe you came up with an idea yourself somehow, you did the literature research, no one did it. How do you actually simulate things? Because in many cases, you need to start with simulation, because if you want to design hardware immediately, that's a huge task. And if you design hardware immediately to test an idea, not only it's very high overhead, you can test only so many ideas in your lifetime, right? So sometimes you really need to go into simulation to really test the idea quickly. If the idea doesn't work out, you adapt the idea to a different way, and at some point maybe you actually manufacture it. So simulation is very nice, and we actually provided a lot of simulators. I'm going to mention some others later, but Ramulator is something that we've been working on for, actually I started this when I was at Microsoft Research in 2006. I started the computer architecture group there, and one of the first things that I did was, I need a simulator to simulate memory controllers. And what I was working on at that time was very similar to what I discussed earlier, memory performance attacks. We showed on real systems that if you have a dual core processor, one application can deny service to another because memory control is unfair. It unfairly treats different applications. So we wanted to provide solutions to that problem. For that, I need a memory simulator. So this is what we designed in 2006, and over time we improved it, and we open sourced it in 2015. And the open source version is very different from what I started with. Our motivation was really, we need a simulator that can adapt to changing landscape of DRAM and memory controllers. There are many new and upcoming standards, many new controller designs, and we need a fast and easy to extend simulator so that we can experiment with things. And you can see some examples over here. This was 2015. Things changed over time. For example, today HBM is a very common memory. It was emerging memory in 2013 or so. Today everybody does HBM, right? Some of them actually did not work out so well, but essentially you have very different memory types, and academia explore even more. So RAMulator is a simulator that's methodical in terms of software design. It provides out-of-the-box support for many DRAM standards, and it's faster than, at the time, fastest open source simulator, and it's modular and extensible. It's very easy to extend. And this is one example study you can do. You can compare different DRAMs for different applications, and you can see which DRAM is better for your application. In fact, we extended the study in a later paper that I don't have reference here. Maybe I'll reference it tomorrow. You can see that some standards are better than others for a given application. And these are averaged across different spec applications. For example, we show that HBM is much better than DDR4 on a majority of the applications over here, because especially the applications that require high bandwidth. Okay, you can do this sort of studies relatively easily. You can actually imagine different memory architectures and code them and see the effect. Now, I wouldn't recommend using RAMulator. I'd recommend using RAMulator 2.0 because this is a huge advance over RAMulator in the sense that we completely redesigned the software. There are a lot of software issues with RAMulator, even though it was the best at the time. Now it's much better and much more easier to use RAMulator 2.0. So I'd recommend people to, if you're interested in memory systems research, take a look at it. And in fact, I should make an anecdote over here. The first author of this paper, who is my PhD student now, he took this course in 2018, and he was a bachelor student who took this course. So he got very interested in the memory systems technology, and he came up with the RAMulator 2.0, I should say. Okay, so there's an optional assignment. I don't expect you to do this, but if you do it, feel free to do it. You can review the RAMulator 2.0 paper. It's only a 4-page paper. It's actually published in Computer Architecture Letters right now. It was a preprint in 2023. You can download it and run it. Hopefully you won't run into issues. We maintain it. And you can email me your report if you're interested. And you can compare different standards for a particular benchmark of your choice. And I'm curious what you find. Okay. Any questions? Yes, go ahead.
Do you use RAMulator for education, like for your courses?
Do I use RAMulator for education in my courses? Yes, absolutely. Yes. So if you look at our courses, you'll find some other assignments that are a little bit harder than this that I gave you that you can do. And RAMulator 2 also couples with other simulators, like processor simulators like Gem 5. So you can actually connect it to processor simulators, different types of processor simulators. I think we have coupled it also with ZSIM, etc. Don't quote me on it, but different simulators it's coupled with. So I can do full system simulation with RAMulator, except it'll be much slower. Okay, so now let's jump into memory-centric computing. So I expect we'll cover this today and tomorrow, because there's a lot to cover in this area. This is the major topic of this course, and then we'll move to robustness issues. So I'm going to go through memory-centric computing. I'm going to remind you some slides that I showed you yesterday. I don't want to cover them again because they're redundant with what we covered yesterday, but this is just to jog your memory of where we are. So this is the second major topic. And I've already said we're having data problems. Data is increasing. There's a huge demand for performance and efficiency. Memory requirements are growing. Compute requirements are growing. And this particular picture is from Cerebrus' CTO. Cerebrus was a very it's still actually. They're designing wafer scale chips, and their goal is to put a lot of compute and a lot of memory together at low latency. We may talk about that. They're putting a lot of SRAM, but the amount of SRAM that you can put on a chip today is very limited. In this case, they have a wafer scale chip like this big, and in that case, they have 80 gigabytes of memory. 80 gigabytes is nothing. Okay. This doesn't mean that they're not a great startup, in my opinion. I think they're trying to do something very, very interesting, except it's not clear if it will be able to cater to the large data sets that we have today, from my perspective. They may have a different perspective. Okay, so I think, as we discussed yesterday, we can generate a lot of genomic data also, so data is increasing. And I think we need to have a thinking about the future. Do we want a world that's sustainable or not so? So as I said yesterday, humans are greedy. We want everything. We want high performance, energy efficiency, and sustainability, but all at the same time. Meaning we don't want to compromise over here. We don't want performance at the cost of sustainability. We don't want energy at the cost of performance. So you don't want to make trade-offs over here. So the question is, if this is the case, and I believe this is much more the case today than 20 years ago, are we designing the right systems going into the future? Are we making the right basic decisions in our systems? And I think you guessed my answer. Essentially, because of the way we're treating the data access, we're really causing great energy waste. We're moving data all across the system, both at the micro scale, from the storage to memory to processor, not processor, storage to memory controller to caches, caches to register files, register file to compute units, and then back. So that's caused a lot of energy waste. This caused a lot of performance loss also, because there's a huge latency associated with it. We try to overcome that performance loss a lot by complicating our systems. What do? We add huge cache hierarchies, as we've discussed yesterday. I'm going to show you a little bit more. What else do? We add a lot of multi-threading. What else do? We add a lot of prefetchers. My PhD thesis was an example of one of those prefetchers. What else do? I'm sure we do a lot more. But basically, we complicate out-of-order execution. Yeah, heavy out-of-order execution. Like the reason why we have very large instruction windows is to tolerate long memory latencies today. Because a cache miss takes a long time, so you need to keep processing instructions to overlap the latency of a cache miss. So our systems becomes a lot more complex. And this cost, usually people don't see, because this is the way we do things, right? We do it this way, our systems are complex. Why are our systems complex? Because we're moving data all around. We're doing the computation, in my opinion, in the wrong place. We're wasting energy, and we're wasting performance. And sometimes, all of these techniques that we've discussed, sometimes they work. Most of the time, they don't work. And I've given you examples of this from big sites, for example, or from Google. Most of the time, the processor is waiting for data still. When they don't work, what did we do? We complicated our systems to waste even more energy. So we're in this vicious cycle today. We're wasting energy to move the data between the processor and memory. To avoid the performance cost, we're complicating our systems. The complexity doesn't give us the benefits of performance or energy. As a result, we waste even more energy. So our systems are in this vicious cycle, and I think realizing that this vicious cycle is really bad for everything that we want to do, performance, efficiency, and sustainability, is really important. So basically, this is the problem. Whenever you're in a vicious cycle, it's really important to understand this is the problem. And I believe this is really the problem. So we're really processing data far away from the data. Okay, so essentially today's processors, computing systems are all processor-centric. All data is processed in the processor at great system cost in the end. And I've shown you examples of this. I'm not going to repeat them. And you can see real examples of real chips. And this keeps coming and coming. So in the end, data is really overwhelming our machines. It's overwhelming our storage and memory capability. That's why we keep adding more and more capacity in terms of storage and memory, more and more bandwidth, etc. It's overwhelming our communication capability. That's why we're adding high-speed interconnects and high-speed memories. In the end, it's overwhelming our computation capability because we're designing actually very capable processors. Some of these processors are really wonders of art and science, right? In the end, they're extremely high performance, but we're starving them because they're really not using their capability as we've discussed yesterday, right? And also data is really impacting robustness, energy, performance, and cost, and we'll see that even more. I've already given you some examples of this. This is just to jog your memory. Basically, the modern processors are always waiting for data. They're not very efficient. So these are the three key system trends that we discussed. Data access is a major bottleneck, energy consumption is a key limiter, and data movement energy dominates computation energy. And we've already given you examples of this, right? These huge numbers in terms of the energy of a data access versus energy of a computation. There's a huge disparity between them today. And as a result, at the system level, most of the energy is really spent on moving data and accessing memory. Okay, so this is where we have discussed. Basically, we do not want to move data. We want to really do the processing where it makes sense. And I don't believe that doing the processing by moving the data to a compute unit far away from the data is the only place where it makes sense. It may make sense, assuming you have very good locality. But in most cases, it doesn't make sense. In most cases, you may want to do processing in the storage, in the sensor, in the memory, in the interconnect, in the memory controller, in the cache, maybe in the register file. In GPUs, they have a huge register file, so don't underestimate that. And sometimes, like maybe 5% of the time, in the compute unit. That's my perspective. So we want to make computing architectures more data-centric. Okay, this is a slide that we discussed yesterday. So the question is how to do this. So we really need to rethink how we communicate with the memory in the end. How do we actually express these functions such that the memory can execute some things? And then it returns the results. So there are many questions over here, as we've discussed last time briefly. Today we're going to go into a lot more depth in this topic, and we're going to see different approaches to this problem, because there's not only a single approach. In the end, we'll need to rethink the software and hardware interfaces to enable this. And there are different ways of rethinking. Do you actually completely get rid of the current interface, or do you actually amend the current interface to take advantage of it? I think both are important for research. How do you design the system software, compilers, and languages to take advantage of it? How do you design your algorithms for it? I will mention theoretical foundations. Yesterday I omitted theoretical foundations, but this is actually really important in my opinion. So we have designed processor-centric systems for 80 plus years of computers. And computing theory. How many people here have taken a theory of computation course? Okay, I see. Not many people. This is also called, I don't know, algorithmic complexity. Okay, let's put that. So when you tried to determine the complexity of algorithms, what did you do? Anybody?
You see how many loops you have.
How many loops? Yes. Basically, you counted the number of operations. In the basic case, it could be how many adds do you do? How many operations do you do? Now, everything I've said, keep that in mind. Is that the right thing to do when we actually determine the complexity of our algorithms, even in terms of performance or energy? Maybe not, right? Yes?
Also the arithmetic intensity.
That's right, yes. You do that, some of that, but you don't use it in many cases, yes. Yeah, that has become later. That came into, the arithmetic intensity came later into the theory of computation. But we don't have a very good theory of arithmetic intensity. It's a metric to use to optimize systems at system level. So if you look at the theory of computing, it's been developed from the very early on. It's very processor-centric. You have the big O notation, big theta notation. They're all really counting operations. We don't have a theory of computing that's much more data-centric in terms of, for example, data movement. And this is a challenge for those of you who may be theoretically minded. How do you develop a theory of computing that's a lot more data-centric? Industry is not going to do this. They don't care. But this is a really great subject for people who can invent the new theory of computing going into the future. I'm not a theoretician myself, and I don't feel comfortable to do it, but I'd be happy to collaborate with any theoretician who's interested in this. Okay, so let me also say that historically, processing in or near memory is not a new idea. This is the earliest paper that I could find on the topic. I'd recommend people to look at it. It's 1969, very beautiful paper by William Coates. They put basically memory, logic close to memory. This is an example of processing near memory, as I will define it. This is another paper by Harold Stone. Harold Stone has a beautiful textbook on high-performance computer architecture. It's old, and from 1992, but it's a beautiful textbook. But he also worked on processing in memory. At that time, they both called it logic in memory. That's why I will keep the term processing in memory and keep it as very general. And then I'm going to define a taxonomy underneath it. Okay, but if you're interested, this is an old idea. Of course, with any old idea, people have worked on it for 60 years or so. You may ask, why is it interesting today again? Are we rehashing the beans? And I would argue that we're in a very different situation today compared to 1960s, 70s, 80s, 90s, 2000s, 2010s. 2020s are very different. Basically, we have nowhere to escape. We have a huge demand from applications and systems, as we've discussed. I'm not going to repeat all of these, I already said that. And we want to improve all metrics. If you want to improve all metrics, I think you have to look at data moment. And also, this is the higher level, right? Applications, systems, algorithms, etc. are pushing us to do something different with memory. At the lower level, technology, we don't have a friend, in the sense that technology is also pushing us to do something different, meaning we're having a lot of technology scaling problems. We're going to examine them, especially in robustness in the latest lecture. RowHammer, for example. We're having issues with scaling memory, and these issues demand intelligence in memory. You need to actually put some computation inside the memory to solve these issues. I'm going to show you a very quick example. I'm not going to go into the detail. But basically, both of these sides, both technology and application and system, are pushing us to do more intelligent things in memory. So we are squeezed in the middle. So RowHammer, very quickly, this is what we're going to discuss later on, but you can induce errors in most DRAM memory chips, and this is a technology scaling problem because cells are so small and cells are close to each other. You have these interference between the memory cells, and as a result, access to one memory cell affects accesses to other memory cells. So you get bit flips. And we've written papers about it, and we've always argued that you need to have more computation on the memory side to fix this problem. Now, the good thing is, industry finally recognized it, and they wrote papers, finally. This is a paper in ISSCC in 2023. In 2023, SK Hynix, which is one of the major DRAM manufacturers, there are only 3 of them, wrote a paper saying that we acknowledge the RowHammer problem, and we're putting computation in our DRAM chips to fix it. So this is a DRAM chip. DRAM chip, people don't want to modify it. That's the mindset. We always argue that you should modify it, but the mindset is you don't want to modify it, but these folks are actually putting computation. I'm going to explain the computation in the latest lecture when we talk about, well, not latest, one of the later lectures. But basically what they're doing is they're putting logic inside DRAM to count how many activations you get to each row, and if the number of activations you do to each row is larger than a threshold, they actually take some mitigating action to fix the RowHammer problem. I'm not going to claim that this fixes the RowHammer problem, but this is a step in the right direction. And this was standardized in JEDEC this year. This is April 2024. They basically call this per row activation counters, and now everybody's going to do computation inside the memory to fix the technology scaling problems. Now, if you can do computation inside memory to fix this sort of problems, what else can you do? This opens a new field. We're putting computation already inside the memory. Why not put some more computation inside the memory, right? So that's the idea over here. So if you're interested in RowHammer and you cannot wait until after tomorrow, we have written papers, you can start taking a look at it. And we're going to talk about RowPress also. Okay, so that's one of the reasons why we're putting computation. The other reason is the application and system level reasons, and I've shown you the processing in memory landscape today. Today we have actually a lot of devices that are capable of computation. I'm going to talk about some of these later on, but first I'm going to talk about processing in memory a little bit more theoretical. And there are many more experimental chips and startups. Yesterday you heard a talk from an entrepreneur that is doing digital processing in memory. I call it near memory processing. But we're going to talk about both near memory processing and using memory processing. And then there are other interfaces that I've shown you yesterday, but we're going to talk about a lot of these. And again, if you want to get an even larger overview, we keep updating this paper on arXiv that has a lot of information about the history plus current state of the art in research, as well as development on processing in memory. We also have a processing in memory course you can attend online. And we've been giving, well, we have an SSD course too. We've been giving a lot of processing in memory tutorials at major conferences. The last one was at ISCA. I couldn't attend, but my PhD student Geraldo gave this. And we have another one coming up at Micro in early November. If you're interested in attending these tutorials, you don't have to go to the conference. You can just log on to YouTube, and it's all live streamed on YouTube. So you can ask questions on YouTube also. Okay. Any questions? I gave you a very quick overview, but now we're going to go into the real meat of the material. We're going to talk about circuits as well as programming. So hopefully you're ready for jumping across the stack. Okay, so I should also say that we need to think differently from past approaches. Past approaches, what they did was, those papers that I've described and many others that I have not described, they basically say, you have memory, you have logic, put the logic closer to memory. This is called processing near memory from my terminology. Basically, you have logic, you design logic as you do today. You design memory as you do today. This is nice because you don't change any of your design processes. And then you put logic closer and closer and closer. The logic can be inside the DRAM chip. The logic can be underneath the DRAM chip in a 3D stacked manner. The logic can be inside the memory controller, a little bit far away from the DRAM chip. The logic can be next to the cache, etc. All of these are examples of processing near memory. But there's something else that people have not looked at until early 2010s. at least as far as I know, and we haven't found any evidence for that. This is more analog. Analog computing is old, of course, but analog processing using memory is something different. So you have logic. Today you design logic, and then you have memory, you design memory. Forget about logic. I don't care about logic. Well, that's a joke, of course. This is memory. This memory has fundamental analog operational properties that can enable you to do computation. And that's the idea of processing using memory. Exploit the analog operational properties of this memory device that I designed as memory to do computation. And then I foster that computation to do even more computation. So this is fascinating, I think. And this is much harder to do. That's why yesterday you heard from an entrepreneur, they said, oh, we wanted to start with analog processing in memory, it was difficult to do. Yes, it's difficult to do. But that's a beautiful topic for research if it's difficult to do. Today it's difficult to do, 20 years down the road, it may be easy to do if you actually enable it, right? So I think we're going to start with this. It's a longer term approach. It's analog processing using memory. And then we're going to talk about processing near memory, which is very interesting also. In the end, I believe we need to combine both to get the benefits, to maximize the benefits of processing in memory. Okay. So let's take a look at this. This is the nature of computation. This basically shows pictures to what I just said. So processing near memory, you can actually have a processor near the bank, the DRAM bank. You can actually have processing inside the vault, etc. Processing using memory, you actually take advantage of the analog operational properties of the memory cells to do computation. For example, you can activate many rows at the same time, as we will see. So this is a longer taxonomy. I'm not going to go over this in detail, and we haven't put this into the paper yet. I would like to put this into the paper. But this was an example of nature. So a processing in memory system is really a tuple of nature, technology, and location. We talked about nature. Technology could be many different technologies. It could be DRAM, it could be flash, it could be SRAM, etc. It could be PCM. And location is location from the system's perspective. Is it in the memory controller? Is it in main memory? Is it in SSD? Is it in hard disk? Is it in tape? And I think all of these places have their role to play in computation. In the end, one can combine multiple different processing in memory types in a system, and each PIM type is a tuple of these. And we're not going to be extremely, let's say, futuristic. We're going to treat memory as an accelerator. So one way of thinking about processing near memory is there is no CPU, meaning everything that you design is an independent agent, and they communicate with each other. And what you have is a really distributed system that can finish a computation via distributed algorithms and distributed coordination. We're not going to go there. I think that's very important to do. That's even longer term. But and that's a paradise for a distributed computing person. If you're a distributed computing person, that's the paradise I would play in. But today, I think if you want to get things adopted, it's a lot easier to make things an accelerator. Meaning, we're going to treat memory as an accelerator. We're designing a lot of accelerators, clearly. Why not have some accelerators on the memory side, or different parts of the memory? So that's the idea over here. And this way you can program it more easily as opposed to going to a completely distributed paradigm. Okay. So what we're going to examine first is processing using DRAM in main memory. And this is called PUD, or processing using DRAM. So let me give you the very quick overview. Okay, we still have time. Basically, we can support a lot of things in DRAM by modifying the DRAM a little bit. And also, even existing DRAM chips support this. So you're lucky to be sitting here in 2024 because there are actually very new results in 2024 that show that even existing DRAM chips support some of these operations that we envisioned by modifying DRAM. And that's really fascinating to me because memory is designed as memory today, right? People use it as loading and storing data. But if you actually think about it slightly differently, you can do computation in it, even existing DRAM chips. You can design your own memory controller in an FPGA with a RISC-V processor and you can do computation. And I'm going to show you some examples of that. But these are the things that we're going to see supported. Majority functions, bulk bitwise, and or not functions, copying and initialization, I'm going to start with that. Random number generation in a true fashion, physical unclonable functions, and by modifying memory you can do lookup table-based computation. And you can do this at low cost in general. And the idea is to use analog computation capability of DRAM. And the overarching idea is really to activate multiple rows, either sequentially or consecutively, with very quick activation latencies. And you can do this even in commodity off-the-shelf DRAM chips that are unmodified. Okay, so you get significant performance energy improvements. So let's start simple. Let's not even talk about computation. Let's talk about data copy and initialization. This is something that's really interesting, actually. It takes a long time in many applications, and there are many reasons why you do data copy. In operating systems, for example, when you free a page, you initialize that page to whatever number, random or zeros, for security purposes especially, so that you don't leak out any data, right? That's one example. There are many, many other examples. If you're actually starting a database, and the database happens to be 20 terabytes, you initialize it. And today it takes a long time, because you need to really make sure that zeros, again, for privacy and security purposes in general. And Google, in their beautiful paper that I mentioned earlier in 2015, they basically said these two function calls, memmove and memcopy, take approximately 5% of the cycles in their entire data center. I think this is fascinating. Only two function calls taking 5% of the execution time, because they do a lot of these because of these reasons. And they basically say, in the paper, they reference our paper that I'm going to talk about, they say this sort of approaches are going to be even more important in the future. Okay. So how do we do copy today in today's systems? Let's assume that you're copying a page to another page. A page could be 4 kilobytes. If you want to copy this white page to the gray page, you go through the processor. You basically bring the data byte by byte into the L1, byte by byte into the L1, do the copy, and write back the data. Now this is clearly high latency because you go through the entire memory system. High bandwidth utilization on the memory bus. Cache pollution, you could eliminate this through DMA today. Unwanted data movement. So a 4 kilobyte page copy via the memory controller, direct memory access engine, not even going through here, takes significant amount of time, 1000 nanoseconds, 3.6 microjoules. Now we're thinking about 10 years old in this course. So pretend that you're, I don't know, 10 years younger or something. Depends on your age. If you're a 10-year-old and if you saw this picture, what would you say? Well, maybe I would say, why not just do this, right? Why are you going through this? Like, I'm touching my ear this way, right? Just touch it this way, come on. Basically, okay, yeah, that's the way of thinking we need, I think, going into the future, right? Basically, just do it in memory. That's the idea. This low latency, low bandwidth, no cache pollution, no unwanted data movement. And this basically takes that 1000 nanoseconds to only 90 nanoseconds and 3.6 microjoules to 0.04 microjoules. And the way to do it in DRAM is actually very simple. So let's go into the DRAM circuit level, low level structure. This is still the architectural level. I'm going to show you the circuit level later. But basically, if you look at a DRAM subarray, this is a part of DRAM, it consists of a bunch of rows. Each row can be 4 kilobytes. And there's a row buffer. The idea is to do 2 consecutive activations. You first activate the source row, which brings the data into the sense amplifiers or the row buffer. Now you've captured the data of the source row that you're going to copy to the destination row. Now if you've allocated the destination row in the same subarray, what you do is you activate the destination row, which implicitly deactivates the source row and connects the data in the sense amplifiers to the destination row. And by using the sense amplifiers or the row buffer as a temporary buffer, you copy from the source row to the destination row, assuming they share a subarray. So that's the idea. 2 consecutive activations, negligible hardware cost, very, very little. And the reason it works is based on the analog charge sharing principles, which I'm going to show you in the next slide. So those of you who don't like the circuit level, you may be uncomfortable with this slide, but I'd suggest you start getting comfortable with these things also. Okay, so I'm going to show you the source level and the destination level. This is intra-subarray, within a subarray. This is the source row. I'm showing you only 1 bit. This is the destination row. This is the bit line. And this is the word line of the source row, word line of the destination row. This is the capacitor, access transistor. Initially, source row is charged. We're looking at 1 bit. We're not looking at all the 4 kilobytes. This is happening concurrently in the 4 kilobytes, but let's take a look at 1 bit. And this is a sense amplifier. It amplifies the charge, basically, whatever it detects over here. So initially, the bit line is VDD over 2, it's a reference voltage. You activate the source row, which connects the capacitor to the bit line, which perturbs the bit line. And the bit line gets perturbed, sense amplifier gets enabled, and sense amplifier amplifies the difference. It basically senses that, oh, there's VDD, high voltage in this source, and there's low voltage on the other end of the sense amplifier. We're going to see that later on. Now if you activate the destination row at this point in time, by deactivating the source row, destination row gets connected to the bit line that's already VDD, and bit line drives its charge, because charge flows from the higher level, higher voltage to the lower voltage, and the capacitor gets charged. Now you copied the source value to the destination value, and you can convince yourself that this happens the same way. If the source was 0, the destination will become 0 in the end. So this is analog operation in DRAM. This works perfectly nice in DRAM. This is how it's supposed to work. We're just taking advantage of it to do a copy. And copy initialization is a special case of copy, right? If you want to initialize a row, you initialize one row to 0 and copy it to other rows, for example. Okay, so you get significant latency savings and energy savings. These are DRAM energy. So you can see the numbers over here. And in the paper we discuss application level impact, benefits. It's pretty good. Now, later work using our infrastructure, these are good folks from Princeton, they actually took our infrastructure, took the row clone idea, and they showed that by violating the timing parameters, meaning there's an activate, pre-charge activate, that happens in DRAM without going into a lot of detail. By violating the activate to activate timing parameter, you can actually do this row clone on real DRAM chips without modifying any hardware. Well, you need to modify the memory controller, but not the DRAM chip. So DRAM chips are already capable of this. And we built on their work to design this FPGA-based prototype, which is open sourced. We completely open sourced it. And the idea is essentially do this thing. So let me give you the very quick idea. You can read the paper for more detail. We have a RISC-V processor on the FPGA. RISC-V processor, whenever it gets a copy operation, we have some changes to the operating system, to the allocation, etc., to the same subarray, for example. RISC-V processor, whenever it gets a copy operation, a page copy, it ships it to the memory controller. The memory controller violates the timing parameters to make sure that the data gets copied from the source page to the destination page. And you can actually do this on real applications using our prototype. It's a little painful. If you work with FPGAs, FPGAs are painful in general, but this takes the pain to a higher level because you need to deal with the operating system and the application and everything. And we see significant performance improvements, as you can see. This is the throughput improvement of copy and initialization. And the numbers here are much larger. And the reason is that the RISC-V processor that we have in the FPGA has very little tolerance to the latency. It's only 50 megahertz. The previous numbers that I showed you actually were smaller because you actually have a lot more tolerance to latency in a heavy out-of-order processor. Okay, this is PyDRAM. Again, if you're interested, you can download the source code, you can work on it, etc. I'd recommend reaching out to us if you have run into problems. So that was one way of copying data in DRAM. There's another way of copying data, especially, so you may ask the question, what if the data is not in the same bank? If the data is in a different bank, then you need a little bit more modification. This you cannot do in real DRAM chips because real DRAM chips, you need to modify the DRAM chips a little bit. But basically assume that there's a shared internal bus between banks in DRAM chip, in a DRAM chip. And if you want to copy data from this row, for example, if you want to copy these 3 bytes from this row to somewhere, to 3 bytes in this particular row over here, you can set this bank to read mode, set this bank to write mode, and basically send a command saying copy 3 bytes from this bank to the other bank. This requires changes to the DRAM interface, but the hardware changes are actually relatively little to do. And we've shown that you can actually reduce latency and reduce energy significantly this way, although the benefits are not as high as what you would get if the source and destination row are in the same subarray. Here, they're not sharing the sense amplifiers. Here you have to go through. Here you're actually doing a read from an internal structure inside the DRAM and doing a write to another internal structure inside the DRAM. But you're not going out of the chip. You're not exercising this huge chip I/O pads. You're not exercising the huge interconnects in the memory channel. You're not exercising anything on the memory controller side. So you're still gaining a lot of performance and energy. Okay, so you may have a lot of questions over here. Can we improve this? Can we enable movement at smaller granularities? Can we do better interbank copy? And the answer to all of those are yes. I may be missing some things over here. That's the potential for innovation going into the future. I'll give you one other example. So increasing connectivity in DRAM. So this sort of data movement is really limited by connectivity in DRAM. Unfortunately, whenever you want to do computation, you need connectivity, communication capability as well. My favorite example over here is the brain, for example. Brain has a lot of connectivity, whereas our modern memory chips have very little connectivity internally. So in this work, we tried to increase the connectivity. So we want to move data inside the DRAM. So let's take a look at how DRAM is organized. We're going to look at a single bank. Single bank has many subarrays. I've already shown you how to do the copy within a subarray. I've already shown you how to do the copy between banks. But how do you do the copy between subarrays of the same bank? This turns out it's unreasonably difficult because there is no connectivity between the subarrays. So what do you need to do? You have to go through, read something from the subarray, take it outside, and write it back to the destination subarray. So this is because of the low connectivity, and low connectivity arises because these subarrays are connected to the row buffer with 64 bits. Okay, the idea is very simple. provide a new substrate to enable wide connectivity between subarrays. Let me give you the very quick idea. Essentially, we add isolation transistors between subarrays. This subarray is connected to this subarray, and they have isolation transistors, so that whenever this isolation transistor is enabled, you can copy data from the row buffer of this subarray to the row buffer of another subarray. If it's disabled, you won't be able to copy data. Now this adds a little bit more cost, but it adds a little bit more connectivity to the memory subsystem in the DRAM. And again, if you're interested, there's a lot more to do in this area. Okay, so this gives you a lot more benefit in terms of bulk data copy, but this also gives you another substrate for data caching in DRAM and pre-charging, which I'm not going to go into. You can read the paper for more detail. And that's the paper that was published some years ago. And we still need a lot more connectivity in DRAM. Okay, any questions? I haven't gone to the computation yet, that's coming soon, but these are some of the other works that try to make copy and initialization faster. And there are lectures also. Yes, please. Oh, okay, sorry.
Like in the other slide,
Yes.
then you said you can only copy from one server array to the other one, like from 1 to 2. And how do you do it if you want to go to 2?
Oh, okay. Basically, you have another, between 2 to 3, you have another set of isolation transistors.
Okay.
Yeah, and we also have express paths between subarray 1 to 3. So I can enable 2 isolation transistors at once. But if you actually enable, so in DRAM you may have 128 subarrays. If you want to copy from 1 to the 128th one, you may need to take multiple hops. Yeah, that's a very good question. Yes?
How much does that reduce the density?
Yeah, so basically this is the answer. 0.8% of the DRAM chip area. And I believe you can optimize it even more.
Really?
Yes. This is based on some industry numbers that also do something, that add isolation transistor for other reasons. But that's always a very good question. Okay. Now in the remaining time, let me introduce this truly in-memory computation capability. As I said, we can support many things in DRAM, and new memory technologies enable even more opportunities. But let me give you how we do this in DRAM. The idea is applicable to other memory technologies as well. I'm going to generalize it later on. So again, this is the same subarray. Now I have 3 rows over here, A, B, C, and I've connected them to a sense amplifier over here. Same picture that I showed you earlier, different colors. And imagine we're going to do this operation across the entire subarray, 8 kilobytes. Assume that we concurrently activate all 3 rows. This is called triple row activation. Now, what happens is if you concurrently activate all these 3 rows will be connected to the bit line with the reference voltage, and they all perturb the reference voltage with the charge level that they have inside the capacitors. And if at least 2 of these cells are charged, you will get the charge state at the end because the perturbation will be actually positive. If at least 2 of these cells are discharged, you will get the discharge state at the end because the perturbation will be negative. And in this case, 2 of these cells are charged, so this is how the circuit, analog charge sharing, will operate. And essentially, the final state is a majority function, a bitwise majority function of these 3 cells. Bitwise majority is beautiful. If you read Donald Knuth, The Art of Computing Programming, chapter 4, he talks about bitwise majority a lot. Now, bitwise majority is interesting. If you set C to 1, you get the AND function. If you set C to 0, you get the OR, if you set C to 1, you get the OR function. If you set C to 0, you get the AND function of A and B. Now you can do bitwise AND, bitwise OR. Now this is looking very interesting. I don't have NOT. This is not functionally complete. But I'm going to solve that problem because I actually have the NOT over here, right? Whenever I activate one row, the complement of that row is over here, whereas the actual value is over here. Okay, so how can you expose this to the higher levels of the program? You can have an instruction that looks like this, bulk AND, A, B, C, it operates at the row granularity, for example. It performs a bulk bitwise AND of 2 rows and stores the result in row C. There's a lot more implementation detail in the paper that I'm kind of skipping over. We reserve some rows and we designate them for triple row activation because you don't want to do this in the entire memory array. It complicates the row decoder and logic and your density a lot. So what we do is basically you row clone A into a row D1, you row clone B into D2, you row clone R0 which stores 0 into D3, and then concurrently activate these 3 rows with a special command to DRAM, and then you row clone the result into C. And this essentially does the bulk bitwise AND operation. If you want to do this in the processor, you have to load and store everything byte by byte to the cache and then do the copy. Do the AND operation in this case, etc. And this is much faster. So how do you get NOT? Essentially, as I said, NOT is over on this here. So we add a little bit more logic into DRAM so that we can feed the negated value. Whenever you activate a row, the complement of the value is on the other side of the sense amplifier because of the way sense amplifier operates, and we connect it back to this dual contact cell. Again, I don't want to go into the details here. This introduces a little bit more area cost, but you can do NOTs in DRAM with little modifications as well. And what is the benefit? In the end, you get significant performance improvement and energy reduction compared to doing this in the CPU. So NOT is actually the fastest. You can do AND and OR, you can do NAND and OR by Boolean logic essentially. And you get significant performance and energy improvements. You may ask, okay, what is it good for? In the end, this is good for potentially everything, as I will show you later on, probably not today, but I will show you the basic results soon. You can rethink your algorithm completely, such that your algorithm is written to take advantage of this sort of block bitwise majority and NOT operations. And we did some of that. I'm going to talk to you about that tomorrow. But there are already some algorithms that are existing that maximize these operations, especially in databases, bitmap indices, for example. I'm going to show you an example. Some databases are designed to operate on bitmap indices. You do a lot of block bitwise AND and ORs and comparisons, etc. Some web search, Microsoft designed a web search engine, Bitfunnel. Encryption algorithms, set operations, we're going to talk about set operations hopefully. There are a lot of algorithms that actually operate on sets or bit vectors. Let me give you an example. This is a bitmap index. It's an alternative to trees. And it's used in databases for performing range queries and joins. So you have many bitwise operations. For example, this is a very simple example. You may have lots of rows in your database, maybe 8 billion or 10 billion, representing the human population, for example. And you may actually categorize them in terms of age. This is the bitmap that represents people who are less than 18. This is the bitmap that represents people who are between this age, etc. And you may have so many bitmaps representations. And then if you want to find some sort of intersection, I want to find who are over 18, who are making more than this much money, who are taking the ACACES class, etc. And then you actually do a lot of bitmap operations. And a lot of databases operate this way, and we can accelerate them significantly by essentially porting them to this sort of substrate. It requires effort, it's not easy, but you get significant performance improvements in queries, as you can see over here. In fact, one of the databases, it's called Bitweaving database. This was designed at the University of Wisconsin by Jignesh Patel's group. We took their database, and their goal was to actually maximize these bitwise operations because they wanted to accelerate these things in GPUs. And if you think about what we're doing, we're actually doing a block bitwise serial parallel, block bitwise parallel operation, just like GPUs would do, except we're doing it in DRAM. We're exploiting the very high parallelism that exists in DRAM. You can do this in 8 kilobytes in a single subarray, but if you have 1,000 subarrays in DRAM, you're doing this operation on 8 million bits concurrently. And we ported their database to actually use our simulated substrate, and we see significant performance improvements on queries. And energy improvements are also commensurate. Okay, there's more in our papers that talk about this. Ambit is the paper that actually covers the NOT operation as well. We introduced the AND and OR first. There are also other papers that we have written. How much time do we have? Okay, minus time. Do you want me to cover one thing that makes it very general, and then we'll start in the next one? Let me very quickly make it general. Who wants one more thing, or who wants to go? That's one more thing. Okay, who wants to go? Don't be shy. I'm not grading you. Okay. So I think who wants to one more thing wins. Very quickly, as I said, you could actually do this for any operation. And this is what we did in this work. This is programmability. So always the question is, if you have a substrate like this, how do you program it? And we wanted to make it easy. And this is the framework that we developed. It's actually looks complicated, but user can now specify any desired operation. If they want to do a block bitwise operation, for example, convolution or matrix multiplication, etc., you can specify it using a hardware structure that looks like this, a circuit essentially, and or not logic. We take this using some quantum computing compilers that are developed by EPFL, by Nani De Michele's group. We actually optimize this graph and have a majority inverted graph. We implement this majority inverted graph using DRAM commands, using row clone, triple row activation, and we do some allocation, etc., registry allocation. And then we create a microprogram associated with that instruction. So this block bitwise operation, it could be a convolution across many inputs, is associated with a microprogram. Now, the user, when they program, or the compiler, can insert this instruction to a program. When this instruction gets executed in the processor, it gets shipped to the memory controller. Memory controller fetches the microprogram and executes that microprogram. So that's a very general purpose system. We don't change the sequential programming model. The programming model is exactly the same as what you would do today, except there's a new instruction there that's implemented in DRAM. And the key is really designing this microcontroller. And again, without going into a lot of details, there's a lot of detail in the paper, and this source code is online, as we will see in the next version. By doing this, we can implement many different complex DRAM operations. We can implement, for example, neural network inference, etc., using the substrate. And we see significant throughput and energy efficiency improvements, as well as performance improvements compared to both CPUs and high-end GPUs. Okay, since we're out of time, I'm not going to cover more of this, but I'm going to introduce in the next lecture how to make this more programmable with compiler support and more flexible. And then we're going to talk about what else can you do in DRAM, and then we're going to go into processing near memory. Okay, feel free to find me in the breaks to ask questions. I'd be happy to chat.